In today's lecture, we are going to study multilinear maps. As you can see from the title, it is we have seen linear maps, and multi is for multi variables. So that means the following. So let me, as usual, we will denote V and W K vector spaces. And we take any finite set, I the finite index set. Normally one can take I to be standard n star n, usual 1 to n, and when you take V power I, that means copies of V indexed by I. This is a product Vi, I in I, and each Vi is V. That means we are taking V cross V cross V finitely many times, as many times as the cardinality I, and this one is indexed by I, and so on. So this is also vector space, this is also K vector space, component wise structure, component wise addition and component wise scalar multiplication, and we are considering a maps from V power I to W, and we will call it I multilinear. Actually K should also be in the notation I multilinear over K, but this is usually dropped from the notation. That means when you fix any ith coordinate, so that means, so call this map as F, it is called multilinear if for each I in I, f of ith coordinate vary like this, xi plus yi, and the remaining coordinates the same, this equal to f xi plus f yi. Similarly for the scalar multiplication, similarly for f of dot 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 a xi, this is a f dot 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 xi. This is true for all scalars, and obviously earlier one all xi yi in V. Then you call it multilinear. This simply means if you look at the map, if you fix all variables and let xi vary, then it is linear in that variable. So this means that is f is k linear in each variable or in each ith coordinate. Then you call such a map to be multilinear map. When W equal to K, then I will keep saying multilinear forms. When cardinality I equal to 1, then I multilinear is same as linear. This is same as K linear. When cardinality I equal to 2, then we will use the word bilinear, and bilinear simply means if I take f of the first coordinate x1 x2 or x1 to be consistent with the earlier notation x1 y1 x2. This is f of x1 x2 plus f of y1 x2, and similarly f of x1 comma x2 plus y2 same as f of x1 x2 plus f of x1 y2, and also the scalar multiplication I will write here for this f of a x1 x2 is same as a f of x1 x2, and for this in the second variable f of x1 a x2 is a f of x1 x2. This is a bilinearity condition. This means linear in this variable, linear in this variable. There are only two variables. So such maps are called bilinear maps. So the set of multilinear maps, the set of all I multilinear maps I will denote by mult suffix k to remember k linearity. I is this index set, V is the vector space, and W. This is a subset of W power V power I, and we know this is a vector space. And it will take 1 minute to check that if I take two multilinear maps, their addition makes sense, and addition is also again component wise, which is coming from here. Similarly scalar multiplication, so that will form a K subspace of this W V power I. This is this we have verified several times such a thing, so this is easy. Now when W equal to K, those are linear forms. So that multilinear forms, that I will simplify the notation and write multk IV. These are multilinear I multilinear forms on V. Forms on V. So they are maps from V power I to K, multilinear in each variable. And okay, so for example, let us see some examples, some standard examples. So as I said earlier, multilinear forms are when I is singleton, I is singleton 1, then mult 1 VK VW. This is precisely all linear maps. It is home K VW. And note, very important case, very important extreme case, if I is empty set, then what should be V power empty set? This should be K, and then mult empty set V W. This will, you can identify this with W, because K to W map is just, they are identified with W. This is actually, one should say this is home K KW, which is this. So this is extreme case but useful for guessing results. Okay. Second example, suppose A is a K algebra. Recall that K algebra means it is a K vector space and a K is a ring, A is a ring, and the ring structure, ring multiplication and the scalar multiplication, they are compatible with each other. So, look at the map, then A power n to A, if I take a tuple x1 to xn is mapped to the product x1 to xn. This is n multilinear. See, this is precisely, these are precisely the distributive properties in the algebra. When I change one of the variable to be the sum or scalar multiply, then this you use the distributive or compatibility properties in the algebra to check that this is multilinear. Okay. Third one, if I have linear forms, so I is any finite set, and for each I, suppose we have given a linear maps Fi, linear forms V to K, K linear form. Then obviously I have a product map from the V power I to K. Namely, if you have a tuple xi, map it to, first you apply Fi to each xi. So these are elements in K and now take their product in the field K. This makes sense. This is the standard notation for this is product map. This product map is called a product map. Is I multilinear. That is, this is an element in mult I V K. It is a multilinear form on V. This is obvious to check because when you change xi to the sum or scalar multiply, it changes here, and then the distributive property in the field K, addition with multiplication and so on. So you can spell it out and then it is multilinear. That is how one checks this one. This is very important. I will use this map to construct determinant functions. I am doing these multilinear maps in order to construct determinant functions, and the determinant functions are very important to study determinants abstractly. Okay. Now just one thing I just want to note, that a general distributive law that means the following: if we have multilinear map F from V power I to W, that means I have a definition. I have given that for each tuple x, I want to use the same notation, xj, j in I, and when I apply F, I get an element in W, and it is multilinear in each variable. So I want to find out the formula for when I want to substitute this each xj. Suppose I have given a family, Vi, I in V, and suppose I have written this xj as the sum of this family A, I, J, Vi, I in I. This is typically will be the case when this Vi is a basis of V. Then arbitrary xj I can write in terms of this, and then I want to evaluate, I want to substitute xj equal to this and find out this. So, I want to expand it. So, that means what, the for f of, and here to get a better understanding, let us assume I is 1 to n. So, f of, I am writing the first coordinate, that is x1, x2, xn, but this is same as I want to plug this value. F of x1 is summation a I and this I is varying. So, I want to vary this, I want to give different names for different AI1, 1, VI1. This I1 is running in I. X2 is summation I2 in I, AI2 to VI2 and so on. The nth coordinate will be summation over running over IN in I, A I N N V I N. And now when I use multilinearity, the AIs will come out from here and from here. So, this will be the sum, it is a big sum running over I1, I2 etc. IN, they are in the set I cross I cross I n times, and then this will come from here, this will come. So, it is a product I in I, A I1 1 okay, A I N N, I do not need a product here then. These products times f of VI1 VIN. So, this is the distributive law. I have not done anything, I have just taken out this sum out, this sum out and this sum out, and then this is sum running over so many indices, and these guys will come out as scalars, and then what remains is this. So, this is very useful when one wants to compute values on the tuples of a multilinear maps. Okay. Now, I want to define something when a multilinear map is symmetric or antisymmetric or alternating. So, for that I will use the notation. Remember, in the last lectures I have spent some time about the permutation. So, when I is a finite set, we have this set of permutations on I is denoted by this. This is the permutation group. On I. And remember, for each permutation we have assigned signature of a permutation, and the signature is either +1 or -1, depending on when we write sigma as a product of transpositions, even number of transposition, then the sign is 1. When we are when sigma is the product of odd number of transposition, then the sign is -1. And we have also checked that this even or odd does not depend on the number is not well defined, but the parity is well defined. This is what we have checked in the last lecture. So, for each sigma a permutation, and for each multilinear map F we can define sigma f. Sigma f is again a map from v power I to w. And what is the definition? The f is a map from, that is f is a map from, multilinear map from v power I to w. And then I want to use this f and this permutation to define a new map. And this new map is nothing but if I take xi, I in I, map it to first variable, the permute the variables and then apply f. So this is f of sigma x sigma I in I. So I get a new map which is called as sigma ff. And note that if f is multilinear, then this map is also multilinear. This sigma f is also multilinear. So we will call f is called symmetric if sigma f equal to f for every sigma. That means f does not change after permuting the coordinates. So this is spelled out, that is f of x sigma I, value on this tuple, value on the value of f on the permuted tuple is same thing as value of f without permuting for every sigma in Si. Then we call f to be symmetric multilinear map. Similarly, we can call f to be skew symmetric. F is called skew symmetric or antisymmetric if sigma of f is not f but up to a sign sigma times f for every permutation sigma in Si. So this means, that is, if I take f and value on the permuted tuple is not the value on f, value of f on the original tuple, but this multiplied by sine of sigma for every sigma. Then we call it skew symmetric or antisymmetric. So in particular, when you take sigma, for example, sigma is a transposition Ij. This is a transposition, that means I is mapped to j, j is mapped to I, and all other elements in I are fixed. Then f of this permuted tuple is nothing but minus f of original tuple. And this tuple, only the ith and jth coordinate will change, and this tuple looks like all coordinates are same. Ith coordinate will become jth coordinate and jth coordinate will become ith coordinate. So this is ith coordinate and this is jth coordinate. So if the two coordinates are switched, then the value changes with the -1. Okay, one more definition. F is called alternating if if for every tuple xi in v power I which has two equal coordinates with two equal coordinates That means there is xi, there is I and j, so that xi equal to xj for the coordinates ith and j different coordinates, the value of the tuple at the coordinates are equal. Then f of this tuple should be 0. Then we call it an alternating mapping. So alternating multilinear, I multilinear. That means whenever you have a tuple with two equal coordinates at different positions, then the value of f is 0, then you call it alternating. Now after the break I will study the relation between symmetric, skew symmetric and alternating maps.